Right now, as you're watching this video, thousands of invisible particles are shooting through your body every second. Some came from the sun, others from ground beneath your feet, and some from bananas in your kitchen. That's just the fact about the world we live in. It is radioactive, but not radioactive as the one that can kill you. Of course, we'll talk about that later on. Now, what if I told you that the same phenomenon that powers the stars helps doctors see inside your body and unfortunately can level entire cities within seconds was discovered completely by accident by a scientist who forgot to put his equipment in the sun? Our story begins with a man called Henry Becquerel in 1896. That was in Paris. The man is a French physicist. Now, Becquerel wasn't studying radioactivity. Nobody even knew it existed yet. He was actually investigating fluorescence. That was the phenomenon where certain materials absorb light and then re-emit it as a different color. Becquerel had been working with uranium salts, which were known to fluoresce beautifully under sunlight. His experimental setup was simple. He would place uranium salts on top of photographic plates wrapped in black paper, expose them to sunlight, and then develop the plates to see the fluorescent patterns. And on February 26, 1896, Becquerel prepared his experiment as usual. But Paris was having a particularly cloudy week, and him frustrated, he decided to wait for better weather and stored his wrapped photographic plates with the uranium salts in a dark drawer in his laboratory. And days passed. Finally, thinking the uranium might have retained some energy from previous sun exposure, Becquerel decided to develop the plates anyways, and he was expecting to see a faint image at best. And to his surprise, when he developed those plates, they were completely exposed, as if they'd been sitting in bright sunlight for hours, but they'd been in complete darkness. The uranium was actually emitting some kind of invisible radiation powerful enough to penetrate the black paper and expose photographic film continuously without any external energy source. Becquerel immediately recognized the significance that wasn't fluorescent. That was entirely something new. The uranium wasn't just re-emitting absorbed energy, it was creating energy from within itself. He then conducted more experiments testing different uranium compounds. The results were consistent with what he found. The intensity of that radiation was proportional to the amount of uranium power. And regardless of its chemical form, this meant that radiation was coming from the uranium atoms themselves, not from any chemical reaction. And keep in mind, at that time, no one had any idea of what this new phenomenon was. So it's kind of strange, even to Becquerel himself. Now, that was the first evidence that atoms weren't the indivisible, unchanging particles that scientists had believed them to be for over 2,000 years. Something was happening inside the atom itself. Now, one of Becquerel's discoveries reached Marie Curie, who was a Polish physicist working in Paris. She decided to investigate that phenomenon for her doctoral thesis, coining the term radioactivity along the way. Now, Marie and her husband, Pierre Curie, made a crucial observation. And what was that? If radioactivity was an atomic property, then other elements might also be radioactive. They began systematically testing materials. What did they find? They found that thorium was also radioactive, another isotope. Even more exciting, some uranium ores were more radioactive than pure uranium itself. And that could only mean one thing. These ores contained unknown radioactive elements. To isolate these new elements, Mary processed literally tons of pitch blende. Picture this. She would stir huge vats of boiling ore with an iron rod nearly as tall as herself, working in a converted shed with no proper ventilation. Over 4 years, she processed over 8 tons of pitch blende to isolate just 1/10 of a gram of pure radium. The beautiful blue-green glow of radium that fascinated the curious was actually a sign of its deadly nature. Mary carried these test tubes of radium in her pockets and kept them in her desk drawer to admire the lights, the beautiful, and, keeping radioactive isotopes in your pocket. Yeah, you might have guessed what will happen. That exposure likely contributed to her death from aplastic anemia in 1934. The Curies shared the 1903 Nobel Prize in Physics with Becquerel for their work on radioactivity. Mary later won a second Nobel Prize in Chemistry in 1911 for discovering radium and polonium, making her the first person to win Nobel Prizes in two different sciences. Scientists immediately began investigating the nature of this mysterious. Like I said, no one really had any idea of what they were. Using magnetic fields, they discovered something remarkable. And what was that? The radiation could be separated into 3 distinct types, which they name after the first 3 letters of the Greek alphabet: alpha, beta, and gamma. Starting with alpha radiation, these are particles that turned out, surprisingly, to be helium nuclei. Essentially, helium nuclear atoms stripped of their electrons, so it only has protons and neutrons. 2 protons, 2 neutrons. The properties, in terms of mass, is about 4 times heavier than a single proton. In terms of charge, it has a charge of +2. In terms of speed, it is 5 to 7% the speed of light. And in terms of range, well, it is only about 2 to 4 centimeters in air. That's the maximum that it can move. And then, how can you stop it? Well, they're so massive and highly charged that they cannot penetrate a single sheet of paper or even the dead outer layer of your skin. They're essentially atomic bulldozers. They're powerful, they're ionizing, but they're clumsy. This is where you need to be very, very careful in terms of, it doesn't mean if it cannot move to foreign air that we can fumble with it. No. While they cannot penetrate the skin, they're incredibly dangerous. If you inhale or ingest alpha emitting materials, or by chance you're contaminated, they deposit all their energy in a very small area, causing cellular damage, severe one, organ failure, multiple organ failure, and ultimately leading to death. Americium-241 found in smoke detectors emits alpha particles. These particles ionize air molecules between 2 electrodes. When smoke particles enter this space, they absorb the alpha particles, changing the electrical current and triggering the alarm. Now let's deal with beta radiation. These guys, the high energy electrons, or sometimes we could call them positron antimatter electrons, they're ejected from atomic nucleus. But wait, there are no electrons in the nucleus. So why do we call them high energy electrons? Well, the trick is this: they're created when a neutron in the nucleus transforms into a proton, an electron, and what we call a neutrino. The electron is immediately ejected as a beta particle. Mass about 1/1836th the mass of a proton. Charge -1. Speed it can reach up to like 99% the speed of light. And then in terms of range, it can move over several meters in air and can also penetrate the skin. You can see the difference between that and alpha. In terms of penetration power, beta particles can penetrate skin and cause radiation burns, but they're stopped by a thin sheet of aluminum or a few millimeters of plastics. Beta emitters like phosphorus 32 are also used in medical treatments, particularly for certain types of cancer therapy. Then for gamma radiation, these guys, they aren't particles, they're rays. Alright, they're electromagnetic radiation like light or radio waves, but with incredibly high energy and frequency. Gamma rays have energies typically millions of times higher than visible light photons. To put this into perspective, if visible light photons were marbles, gamma rays photons would be cannonballs. In terms of its properties, it has a mass of 0, the pure energy. It has no charge, it travels at the speed of light, and it is extremely penetrating. Right now, gamma rays can penetrate several centimeters of lead or meters of concrete, and that is why nuclear facilities use such thick shielding. They're also usually emitted when a nucleus transforms, or when we can say transitions from a high energy state to a low energy state, often after alpha or beta decay has left the nucleus in an excited state.